decided not to turn on my video. I don't want to challenge it too much. So just to use your imagination on that front. I'd like to talk today about the Seabat Normalised Backscatter that we produce. And before I start on that, really, I'd like to just give an overview of the multibeam range that we're talking about, right? So the Seabat multibeams are generally a shallow water multibeam, right? So the frequencies run between 200 and 400 kilohertz, or 150 and 400 kilohertz, or between 400 and 800 kilohertz. So generally high frequencies, shallow water operations we're looking at. Then we have the hydro sweep systems. That's really deep water systems. But the normalized backscatter that I like to talk about today really relates to the Seabat products. And it is considered, we refer to this as a modular system because we have the different components and you can kind of mix and match and make up the system, right? So you have the different processors and each with their own uniqueness, be it waterproofness or integrated GNS-INS or small form factor, low power, etc. On the receiving front, we have the different receivers depending on the frequency used or the size of the receiver, and similarly for the transmitters. But then, of course, from a backscatter point of view, what's important is however to match these components, that the backscatter is consistent, right? And that's an important thing that we have worked a lot on is really trying to keep that backscatter consistent, because of course when users want to infer their results, they don't want to see effects of the system that was used to collect that data. They just want to really see the actual backscatter changes. So in terms of software also, there's just one software that actually operates for all of these systems, but all the number crunching, all the like the beam forming and the snippets generation and the normalized backscatter generation, all that happens on the processing end. That's really where the heavy processing power is needed. So then looking at backscatter, this is an image that is probably quite familiar. We've all seen either this image or similar ones. We've all had data sets like this. When my daughter looked at it yesterday, she said she saw a baby unicorn. But other than that, I think you can really tell differences in backscatter, right? Even though on its own, the image isn't great, you can still see the differences in backscatter. If you want to see low or weak reflecting seabed against strong reflecting seabed, you can see that on a scale of hundreds of meters. If you want to look closer and see maybe like cold water corals and habitats for those and that type of stuff, then it's not so useful. If you want to look within a survey line or compare lines, or even better, if you want to do repetitive mapping, then this is not useful. There's lots of stuff going on, lots of unknowns happening here. And that's for us as a manufacturer then the task to see can we make something that is more consistent so that the user doesn't need to be troubled with what settings were used, because really in an ideal world those things are really irrelevant for the user. The user just wants to get the data and then make their conclusions based on what they see on screen. They don't want to have to go through a whole process where they have to reverse engineer back to an original signal. So we did a lot of work on this to create what we now refer to as normalized backscatter. But I think it's important just to realize that a multibeam doesn't really measure dB values, right? It's just at transmit we send an electronic pulse to the ceramics that converts it to an acoustic pulse that interacts with the seabed. It comes back, and at receive the opposite happens. So we have that acoustic pulse that excites the ceramics, and that converts it to maybe a voltage, a minute voltage, a tiny value. And then that goes through a lot of processing, right? A lot of processes to ultimately give you a backscatter value in dB, right? But what happens in that process is difficult to understand. And when we looked at this a number of years ago for our old 7K systems, we realized that we didn't have a good handle of what was happening, right? So since then, we've made a lot of improvements. So for example, on the transmit size, on the source level side, now if the user would actually increase source level by 5 dBs, we are confident that the equivalent of 5 dBs is being used. On the same side, on the receiving side, I mean, we see the same trend. So when we look at the old systems, they were not. So if we look at this graph here, on the left here, this is let's say the intensity of your backscatter value just registered as a machine number, right? And then if we look at any value and at a given range, at a given gain value, you could relate that to a sound pressure, but very quickly the curve flattens out. So very quickly you'd be receiving data that sits in this curve, and it's just, yeah, you can't really make anything of it, right? It's not linear, and that was really the problem with our 7K systems. So with the T series, we do have a much better handle on that. The first change that you'll notice is that the dynamic range has increased. So we now has a dynamic range, 15-bit dynamic range. And that was also a problem with the older systems, because you would quickly have that you're clipping data, right? And we don't have that. So we have much more resolution now on that bigger dynamic range. And we have these linear relationships now. We can relate this back. So that was it seems like a little thing, but that takes a lot of the redesign of the receiver and the ceramics and all the signal processing in between as well. So other things that we're doing is we associate all our backscatter data with footprint calculations. So it is corrected for the area of the footprint, but we do supply this information. So if you wanted to use your own footprint calculations, you can reverse engineer that to the original backscatter value, and then use your own footprint calculations. That's all that data is available in our records. And then finally, we have this product what we call the normalized backscatter. And the reason why we talk about normalized and not calibrated backscatter is because we've seen in the production of our systems that we're very consistent in how we produce these systems. We have a very tight handle on the supply chain of components. So the parameter set that we deliver applies to a receiver and a system, rather than a particular serial number of a system, right? So that's why we call it normalized backscatter. If you want to have it calibrated, we can calibrate in the tank, but to do this mass for all the systems that go out, that means a lot of time, a lot of cost that's involved. So that's not what we want to be offering. So that's why we refer to it as normalized backscatter. And the benefits of this are really twofold. This is, first of all, you can afford it now that the user can change the settings, and it corrects the backscatter signal. So you don't have to run it with fixed settings. And the second benefit is that now we can actually associate a dB value to it, and we're more confident about that than we were before. So some examples of how consistent is it. So here's some repetitive angular response curves. So if we look at, for example, the transmit, the left one where we have the drop angular response curve for different transmit beams, transmit powers, you see that it's quite consistent within nadir to about, let's say, 60 degrees, 40 degrees. You know, the spread is about half to 1 dB. And then after that, it gets a bit bigger. So it goes up at about to 2 dBs. And then receive gain, we see the same. There's actually different data from the receive gain. That's why the angular response curve looks a bit different. But again, you know, the spread at the different receive gains is about 1 or 1.5 dBs. And that's encouraging, that type of spread, because if we think about classification, which is the end goal, right? If we think about things like gravel and sand and silt, that is roughly about 10 or 5 dBs apart, right? So it is a spread that is encouraging if we think about what we could do with it in the future. So this is an example of data that I collected where I'm running back and forth, and I just want to show you kind of the power of the normalized backscatter in that sense. So every line that I'm running here, I'm changing some value. So whether it be the power, the gain, absorption, and spreading, and really see those shifts in the backscatter, right? It stays the same because it's all corrected for. You might notice two situations where there isn't quite an abrupt change, right? And this is where we're just amplifying it too much, right? We're giving too much gain and it reaches saturation levels. And that on its own doesn't have to be an issue because the user will be alarmed when the beams are in saturation. So the user can pay attention to that. This last line, we're using a feature called tracker, and tracker is like an autopilot, right? And you can see also when we use tracker, backscatter levels remain the same. They're unaffected. And backscatter is quite a unique feature in that sense, and very useful for a lot of our users for mainly two reasons, really. Either they are just not experienced enough to run the system, or they just don't have enough time to be babysitting the system, right? There are things going on during a survey, right? So you don't want to be taking care of all the different settings. And from my point of view, I think the user shouldn't be troubled with what the settings really are, you know, with the power and pulse length and all that. That's just stuff for, you know, not for the average user, right? So with tracker, you can control that, and you don't have to worry about that. So I'll show you a little image or clip where you'll see the effect of normalized backscatter. And I think for this audience, particularly interesting is to look at what happens with things like gain and absorption. You'll see that I start the image and it's or the video and it's very scrambled, and then tracker is turned on, and then you'll see that the gains and such gets adjusted, and tracker just senses the differences in the Seabat response and adjusts it so that you have the best settings for both your bathymetry and your backscatter as well. So you see that here, this is all scrambled. The user sets tracker on, it snaps to the right range, and you see the ringing effect. See how that decreases, and that's because slowly tracker starts to realize, oh, we don't need that much gain. We can turn it down. And same with absorption, spreading, pulse length, all those settings. You can let tracker just adjust that, and it does a very good job in controlling all those things. And the reason why I show this is because this is also very powerful when you use it in combination with normalized backscatter. So in this example, we're going slope, and the depth difference is between 17 meters depth difference. And normally, as you would go down that slope, you would need to, you know, you'd have more losses, right? So you need more gains. You maybe apply more power as well. So you could normally be changing those settings, right? And this is then the effect to the backscatter, right? So if we look, we're going down the slope, and you can see this is what everybody wants to prevent happening, is all those different backscatter operational settings, and you see the effect to your snippets data. And here you can see the actual value. So you can see how tracker constantly changes all these things. And the idea, of course, with using normalized backscatter is that this is corrected. This is then a bunch of lines, right? And again, this is what you don't want to deliver a data set like this. So that's your standard snippet. And this is then the normalized backscatter. And you can see the difference is quite obvious. There's like a wavy pattern here. This is real data, and it isn't removed. It's retained, but we're not seeing any of the operational settings anymore. I just also want to get a moment to talk about hydro sweeps and the backscatter for what we do there, because although we don't have normalized backscatter for the hydro sweep, it is something that a lot of our users are really interested in, and we do try to come up with ways to ensure that they can collect consistent backscatter. We have essentially two different modes, really. We have an sort of like an automated mode, which is ideal for a bathymetry point of view, where you want good resolution and wide coverage, but it's not ideal for your backscatter. So we have a different mode where you can use based on fixed depth range. It uses the right settings so that your backscatter doesn't change all the time. And you can see that effect here. We logged this data overnight. We weren't actually present. This was during the night shift, and we're covering 300 meters to 4,000 meters. And across such a large depth range, we're seeing consistent backscatter data. This is a real-time mosaic that's being made in our software. You'll see the sectors. That's because this isn't corrected for your beam pattern, but not a drop in different. You don't see any sonar operational settings that affect the backscatter. And also for the hydro sweep, we use the same software then for the deep water systems. This has improved immensely compared to the old software that we used to have. It's much more intuitive to operate the system, and you can get now you get nice waterfall displays from your snippets backscatter, for your side scan backscatter if you present it that way. You can color code data to the backscatter levels, and the saturation monitor as well. So is a big improvement from where we were coming from. And there was some talk earlier, or various talks touched on the topic of data formats. So I just want to address that as well. We have our Teledyne S7K file format. So that's all our data goes in that file format, whether it's a Seabat or a hydro sweep, it all goes into the same format. This is a format that's developed and maintained by Teledyne, and it's supported by all the third-party softwares, right? It is very well documented. We have the 7K DFD is a document that describes all the different records. All the data is there. If a user would change anything online, if they would change a power value or touch the slider bar, it gets recorded and to the S7K file. So all of that is available. And we also have sample code, library files and such. That's also all available. It used to be on GitHub, but we're no longer allowed to distribute or use GitHub. So right now, you can use this link, or ping me an email, and then I can send you a bundle, and that has all of it in it. If you want sample files, for example, we have that as well. So just also mention some references here. We have quite a few documents that describe normalized backscatter and general backscatter for the Seabat system. So if you really want to dive into the nuts and bolts of how everything works, I'd suggest referring to some of these references. They'll probably have most of the information that you're looking for. And then just before I leave, I just wanted to also mention that we have a software update coming up that will allow multi-frequency backscatter for the T series. It's just a software update, and updating is also quite a simple process. So if you're interested, reach out, and then we'll send you the details. And running it is also quite simple, where online you would just select the start and end of your frequency range and the step value, and then it would just cycle through. All the different frequencies. And so as you can see, it's also supported by QPS FMGT to read all that data in. There's nothing has changed to the records, by the way. The records are all the same. This is like I said before, whenever there's a change, it registers in the 7K records. So those existing records are just read in, and it will tell you which frequency a particular ping was associated to. Okay, yeah, that was me. Thanks for the attention, guys.
Perfect, thank you, Pim. Perfectly on time.
Perfect.
I have a question.
We have questions. Xavier has a question. Whilst we set the next speaker up.
Yes, Pim, I understand what you mean by this